Okay, quantifying heat and work. So system absorbs heat, its temperature is going to increase. It'll increase by delta T. So delta T is the change in the temperature of the system. That increase in temperature is directly proportional to how much heat energy was absorbed. The proportionality constant is called the heat capacity. So your book is using capital C for the heat capacity. And the unit of that would be joules per degree Celsius or joules per Kelvin. So the amount of heat absorbed is equal to a proportionality constant times the change in temperature. Q would be in joules, and delta T would be in degrees Celsius or in Kelvin. And so the units here need to be joules per degree Celsius. So we can also refer to heat capacity, that's C, as the amount of heat required to change the temperature of a system by 1 degree Celsius. That's the heat capacity. So a larger heat capacity means that the same amount of heat will cause a smaller temperature increase. A small heat capacity means you'd have a bigger temperature increase for the same amount of heat. So the heat capacity depends on how much matter there is. If you think about trying to boil some water to make spaghetti, if you boiled 2 cups of water or 12 quarts of water, it's going to take a lot more energy to get the big pot of water to boil, right? So the heat capacity depends on the amount of stuff. So heat capacity is an extensive property. Extensive properties depend on how much matter there is. So the mass of a piece of wood depends on how much wood there is, right? You cut the piece in half, the mass changes. That's an extensive property. Intensive properties do not depend on how much stuff there is. The color of the wood does not change when you cut it in half, right? The density of the wood doesn't change. Those are intensive properties. So heat capacity, being an extensive property, isn't all that useful because it's going to be different for every sample because of their different sizes. So we make it into an intensive property, and we call it specific heat capacity, C sub S. That's an intrinsic property. It's the intrinsic capacity of a substance to absorb heat. The heat capacity, so it depends on the amount of stuff. It also depends on what the stuff is. So we define specific heat capacity as the amount of heat needed to raise the temperature of 1 gram of that substance by 1 degree Celsius. So this has units of joules per gram degree Celsius, or it could be joules per gram Kelvin. The molar heat capacity would be the amount of heat needed to raise the temperature of 1 mole by 1 degree. So that would be joules per mole Kelvin. These are intensive properties. It doesn't depend on the amount of stuff, because we factor that into the problem. Now your book uses C sub S for specific heat capacity and C for heat capacity. We actually don't use heat capacity much at all. It's always specific heat capacity. So I may get sloppy and just write C, and I mean specific heat capacity. And then in the experiment we're going to do on this chapter, I believe that they use either C or S, and again, it's the specific heat capacity. That's the only one that's actually any use to anybody. Okay, so this gives rise to an equation that's useful. So we can say that the heat is equal to Q. Q is what we use to refer to heat. Q equals mc delta T. So m is the mass in grams, C is the specific heat capacity in joules per gram degrees Celsius, delta T is the temperature change in degrees Celsius. So without all the extra stuff, Q equals mc delta T. We're going to use that one a lot. You should memorize that. It kind of looks like MCAT, right? The delta kind of looks like an A. So sometimes we'll say Q equals MCAT, MC delta T. Here is a table from your textbook giving specific heat capacities of some common substances. The units here, joules per gram degree Celsius. You do not memorize these. Don't memorize those. I'm always getting questions. Do I need to memorize? And you give me this weird table. No, you don't need to memorize it. Memorize this, okay? Memorize this equation. Do not memorize this table, okay? Waste of time and mental energy. If we need these values, we go look them up, okay? So water, well, let's go back and look at that real quick. Here we've got water. Water's specific heat capacity is 4.18 joules per gram degree Celsius. Look at all the rest of these. The different metals here, ethanol, alcohol, glass, granite, sand, all of these have heat capacities that are much smaller than water, right? Oops. This high specific heat capacity of water is an important part of our planet. It regulates our temperatures. So here we have a picture of the Golden Gate Bridge in San Francisco. I lived in the Bay Area for about 3 years. The weather there is very different than the weather here, right? So at the Golden Gate Bridge, it's always like 50, 60 degrees, seems like. It never gets really hot, it never gets really cold, because it's surrounded by water. And the water has a very high heat capacity. So as the sun beats down, it takes more of that sun energy to raise the temperature of water than it does to raise the temperature of dirt or concrete or asphalt or air even. And so the water doesn't heat up very much. So that keeps the air above it from getting very warm. And then as soon as the sun goes down, and in the summer we all relish that time, the sun finally goes down and it just like the temperature starts to drop instantly, right? It's wonderful. So we no longer have that energy coming in from the sun. It can get really cold here at night. In the Bay Area, it never gets really cold at night. They don't get frosts because they've got this big reservoir of water that as the air gets colder, the water's warmer than the air and it releases back that heat energy into the air. And so the San Francisco Bay causes the temperature in the Bay Area to not fluctuate as much as it does here. We use water as a coolant because it's capable of absorbing a lot of energy, a lot of heat, without raising its temperature as much. So that's why we use water with antifreeze in it as a coolant in the car, is to keep the engine cool. Okay, so let's do a problem with that MCAT equation. When I was a kid, we called these story problems. Doesn't that sound friendlier than word problems? It's a story problem. It's a problem about a story. Or a story about a problem, I don't know. So this kind of has a story. To determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. She first weighs the rock and finds it has a mass of 4.7 grams. She then finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 degrees Celsius to 47 degrees Celsius. Find the specific heat capacity of the substance composing the rock and determine whether the value is consistent with the rock being pure gold. Specific heat capacity is an intensive property. It can be used to identify a substance because it doesn't matter how much you have, the specific heat capacity is the same. Okay, so we read all the words, and let's pull the numbers out. So I've got 4.7 grams. I'm just going to write them down, and then we'll figure out what they mean. And 57.2 joules. And we have 25 degrees Celsius and 47 degrees Celsius. So specific heat capacity should make us think, well, Q equals mc delta T. That's probably going to come into this. So let's see if we can label some of these things. 4.7 grams is what? The mass. So we'll call that M. How should we label 57.2 joules? (57.2 joules of heat). This is mass, specific heat capacity, change in temperature. What's the Q? Heat. Okay, Q is heat. I don't know why it's Q. You'd probably prefer it to be lowercase h, but that's Planck's constant, so that was taken. Here we have two temperatures, right? So these are both temperatures. So this is T, and this is T. So we've got M, Q, two T's, and what are we trying to find in this equation? C sub S, right? The specific heat capacity. So what's delta T? The final is the change in temperature, the final minus the initial. Which of these is the final temperature? 47. And so the other one must be the initial. And we get that from the words. The temperature rises from 25 to 47. Okay? So then we can calculate the change in temperature, delta T equals the final temperature minus the initial temperature. Sometimes this is positive and sometimes it's negative, and it matters. So here we have 47 minus 25, and I think that's 22, right? Yeah. So that's our change in temperature. Okay. Nice. But I want C sub S, and this equation is set up for finding Q. So I need to rearrange the equation. We rearrange equations a lot, don't we? Okay, so I'm going to divide by M, and I'm going to divide by delta T so that I can get rid of those things on that side of the equation. And if I do that on one side, I have to do that on the other side. The delta T is kind of lost under the Q there. Excuse me. Specific heat capacity is going to equal Q divided by M times delta T. Okay? So I have Q, I have M, I have delta T. I'm just going to plug them in here. So Q was 57.2 joules. M was 4.7 grams. And delta T was 22 degrees Celsius. So I look at those units. Does anything cancel out? No. But that's okay, because specific heat capacity has weird units. Okay, so 57.2. Be careful because you're dividing by two things. Divided by 4.7, divided by 22. I'm looking at this and thinking this number should have two significant figures, 0.5531. So I'll round that to 0.55. And the units are just the units that are sitting there. Joules over grams times degrees Celsius. So that's the specific heat capacity. Is that consistent with the rock being gold? We can't tell from this slide. We need to go look at the table. So we look at the table and we see that gold is right here. Now gold has a specific heat capacity of 0.128. Is the rock gold? No. Can we tell for sure what it is? No. No, we can't. It's not matching up with anything on this list. It could be a mixture of things. It could be something that's not on the list. But we can say for sure it's not gold, okay, because it's not even close. Any questions? So you've got two objects at different temperatures, like the burrito and the Go-Gurt in your lunchbox. The heat flows from the high temperature to the low temperature, and it keeps doing that. As the hot thing gets colder, the cold thing gets hotter until it gets to the same temperature. The amount of heat energy lost by the hot thing equals the amount of heat energy gained by the cold thing. So we can use this to our advantage. If we take a block of metal that's hot and stick it in a beaker of cold water, what's going to happen to the temperature of the water? It's going to go up. And what's going to happen to the temperature of the metal? It's going to go down, right? So the metal is transferring heat energy to the water. The amount of heat transfer from the metal is equal but opposite in sign to the heat energy gained by the water. Okay? So the Q is the same number, it's just that the sign is different. The exact temperature change that's going to occur is going to depend on how big the piece of metal is and how much water there is, and the specific heat capacities of the metal and the water. So Q for the metal equals negative Q for the water. That's the same as negative Q metal equals positive Q water. It's just that they are opposite in sign. One's negative, one's positive. Q for the metal, Q equals MC delta T, is the mass of the metal times the specific heat capacity of the metal times the change in temperature for the metal. Over here for the water, the mass of the water times the specific heat capacity of the water times the change in temperature for the water, and a negative sign in there. Any questions about that? Q for one thing equals negative Q for the other because all of the energy is being transferred from one to the other. Q for this one is MC delta T, Q for that one's MC delta T. So I just took MC delta T equals negative MC delta T. Let's practice that. A block of copper of unknown mass has an initial temperature of 65.4 degrees Celsius. The copper is immersed in a beaker containing 95.7 grams of water at 22.7 degrees Celsius. When the two substances reach thermal equilibrium, the final temperature is 24.2 degrees Celsius. What is the mass of the copper block? And my thought is, why don't you just put it on a balance and find out? But we have to do the problem. It can be helpful to draw a picture for something like this, because we've got a lot of temperatures in there, right? So let's do this. Let's draw. So we've got a beaker with water. Okay, so there's my beaker, and water's blue, right? So it's got water in it. It must be an earthquake or something. What do we know about the water? Do we know the mass of the water? Yeah. The mass of the water is 95.7 grams. Right? What else do we know about the water? Its temperature, it starts out at 22.7. So its initial temperature is 22.7 degrees Celsius. Do you see how I'm getting that out of there? Interpreting the problem is usually the hardest part of this. If I just gave you the numbers, you could stick them into the equation, right? It's pulling it out of the words that it's tricky. So here I've got this number and that number taken care of. What else? I've got the block of copper, and I have an initial temperature of the block of copper. Well, copper is kind of copper colored, right? So here's the block of copper. And what do I know about the block of copper? I know its initial temperature. So initial temperature for the copper is 65.4 degrees Celsius. Do I know its mass? No, that's what I'm trying to find. So mass equals question mark. So the final temperature is 24.2 degrees Celsius. The final temperature of what? Both of them, right? The one is hot, the one's cold, and heat is transferred until they're the same temperature. So T final for the copper is 24.2 degrees Celsius. And T final for the water is also 24.2. Okay? So can we calculate delta T for each of these things? Yeah, we could do that. Since I've got the blue marker going on right here, I'm going to do that one first. So delta T for the water is the final minus the initial. So that's going to be the 24.2 minus 22.7. Better do that on the calculator. 24.2 minus 22.7. 1.5 degrees Celsius. And then I can calculate the delta T for the copper. The final temperature, 24.2, minus the initial temperature, 65.4. So do that on the calculator, 24.2 minus 65.4, and that's a negative number. Negative 41.2 degrees Celsius. Is it okay that that's negative? Yeah. The change in temperature was negative, meaning that the copper went from a high temperature to a low temperature. The change in temperature for the water is positive because it went from a cooler temperature to a warmer temperature. Okay? You're always going to have one positive and one negative. That's where the difference in the negative sign, difference in the sign comes from. Okay, so, well, what can we do with this? Well, we're probably going to need to use Q equals MC delta T. So Q for the copper is MC delta T, and Q for the water is also MC delta T, right? So what I can say about what's happening here is that the heat lost by the copper was gained by the water. So I could say that Q, actually I'm going to do it over here. Q for the copper is going to equal, it's going to be the same size as Q for the water, but the sign is going to be different, right? So Q for the copper is MC delta T. So that's, MC delta T. And Q for the water is MC delta T for the water, right? So I'm going to take off just the Q here. And that's MC delta T. The heat lost by the copper is equal to the heat gained by the water, but the sign is different. Any questions? Once you see this, it's beautifully simple. But until then, not so much. So we did all of that. What are we trying to find again? We're trying to find this M. Okay, so we've got this equation that's got all these things in it. We need M by itself, right? So I'm going to divide this side by CS and delta T, and I'm going to divide the other side. Now, I'm using colors because I can. If you don't have colors, then you have to use subscripts. And so you might use M for the metal and W for the water, or Cu for the copper and H2O for the water. It gets kind of messy. And I'm just going to use this because I can. So what I'm going to do is I'm going to divide both sides by CS delta T. I'm going to divide this side by CS delta T. This CS is not the same as that CS. This delta T is not the same as that delta T, okay? So they're not crossing off on that side, but they are crossing out or canceling out on this side. Well, they are on my screen. Okay, right? So we're thinking, well, okay, great. That's a bit of a mess there, isn't it? What to do. Okay, I don't need this anymore. So I'm just going to copy this over down here. So I've got the mass of the copper is equal to negative mass of the water, specific heat capacity of the water, change in temperature of the water, divided by specific heat capacity of the copper, change in temperature of the copper. Lots of things to keep track of here. So what's the mass of the water? This one right here, 95.7 grams. What's the specific heat capacity of water? I don't know. We'd go look it up on the table. It's 4.184 joules per gram degrees Celsius. What's the change in temperature for the water? 1.5, right? And then that whole thing is divided by the specific heat capacity of copper. Gotta go look it up. .385. 0.385 joules per gram degrees Celsius times the change in temperature for the copper, which is negative 41.2 degrees Celsius. I want to check that the units are working out okay. There's no funny business. Well, I've got degrees Celsius. Those cancel out nicely. And here I've got joules per gram degrees Celsius. And down here I've got joules per gram degrees Celsius. So I can just cancel all of those at the same time. What am I left with? Grams. And I'm trying to calculate mass. So that sounds like a good deal. Be careful when you put this in your calculator. So what I have is negative 95.7 times 4.184 times 1.5 divided by 0.385 divided by negative 41.2. So mass equals 37.86 grams, which I would round to 38 grams. Any questions? Could you have a negative mass? No, you can't have negative mass. You can't have negative volume.
Water the same as calories for a reason, or?
Yeah, the specific heat of water is the same number as the conversion between joules and calories. A calorie is the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. That's how the calorie is defined. So if a calorie is equal to 4.184 joules, then the specific heat capacity of water is 4.184. You can express specific heat capacity in calories, but usually we do it in joules. So be careful with the negative signs. They're important. Any other questions? And we'll save that for another day.